Hello everyone, welcome back to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC geoscientist exam, right? And in that we were discussing about our organic chemistry portion. So already 3 of the parts we have discussed on this particular channel. Now this video is gonna be the part number 4 in that particular series. Okay. So let us begin with the fourth part now. So before starting the class, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts, and do share it with your friends as well. Okay, so the first question of this part is there on your screens. This is your question number 91. Already 90 questions in the first 3 parts we have discussed. If you have not watched that, I'll provide you with the link to that in the description. You can have a look for that as well. Okay, so now let us begin with the solution to this one. So here this question, it says we have to predict the major product that is formed in the following reaction. So in the reaction you can see a molecule is given, that is your substrate. There is a presence of this alcohol moiety in this, and this is treated with your reagent, that is your HCl. That is basically the acidic medium has been provided, and along with that we are having is the heating condition. So how is the reaction gonna proceed in this? So you can see this oxygen molecule that I'm having, it bears a lone pair of electrons on this, right? This lone pair of electrons can easily abstract this proton from this acidic species, that is your HCl molecule, right? So after the protonation it will be getting converted into the water, right, like this OH2, and here this lone pair of electrons oxygen has donated, so a positive charge will be coming on this, and here this methyl groups, they are present as it is. Right now in the initial molecule, if you see OH that was present, it was not a good living group, but water, it is a good living group, because after the loss you are getting a neutral molecule is leaving basically from the reaction medium, so it can easily leave. So this will be leaving from the medium, resulting into the formation of a carbocation. So this carbocation species we will be getting like this. Here a positive charge it will be created. Here your methyl groups, that is remaining as it is. Now this carbon center that is containing the positive charge, it is attached with the 2 carbon centers. So this is my secondary carbocation. Right? It can further undergo the rearrangement. Here the proton that is present on this carbon center, it can be shifted over here, because after the 1,2 shift you will be getting is a stable carbocation formation. Right, 1,2 shift if we do, we will be getting is this species. Here the positive charge will be formed on this carbon center, and the hydrogen group it has shifted over here. Here the methyl group it is remaining as it is. So this carbon center that we have generated now, this carbon is attached with the 3 carbon centers. So you have got as a tertiary carbocation, which as compared to the secondary carbocation is more stable in the nature. Right. Next, further you can see here is again the presence of this hydrogen atom. Further rearrangement and it is possible, because for the while if you see how many hyperconjugating hydrogen atoms are present. So here it is 1, 2. This is 3 and 4, and this is 5. So 5 alpha H we are getting it at this particular site. Now after if we do the rearrangement, now this hydrogen atom if you shift over here, that means again 1, 2 shifting if we do it. So we will be getting is this particular carbocation formation. Here this species is as it is. Here the methyl group it is present, and its hydrogen it has shifted, so a positive charge is coming on this carbon center. So again you are getting is a carbon attached with the 3 carbon atoms, so a tertiary carbocation. But here if you count the number of alpha H that you see it, so 3 of them are present over here, 4 and 5 is on this carbon, and 1 carbon atom, 1 hydrogen atom on this particular carbon center. So here we are having is 6 alpha hydrogen. So as compared to the previous one, after the 1,2 shift we have got even more stable carbocation. The reaction further will be proceeding through this one now. So this species you have got it. Now in the HCl moiety that we were having, the Cl negative that will be acting as a nucleophile now, and will be attacking over this carbocation species. So the species finally you will be getting is this one. here the methyl group it will be present, and here will be the presence of this Cl group. So this is gonna be our final product. So now you can match it from your options. So here I can see that this is in the option number B, that is matching. Here the methyl group and Cl are on the same carbon center. So this is gonna be the answer to your question. Okay. So I hope this one is clear. Let us move up on to the next question now, that is this one. So in this question they are saying which of the following substrate will be more reactive in the solvolysis condition. Solvolysis basically means the SN1 reaction they are referring to, using the formic acid in the pair X and the pair Y it will be respectively. So this is not by, this is y. So two of the pairs have been given. We have to predict which one is basically gonna give a faster rate of the SN1 reaction. So in the SN1 reaction, basically you can check the stability of the carbocations, right? So that the one that is gonna have the more stable carbocation will give a faster rate of the SN1 reaction, right? In this, if in the pair X, if I see, so OTS group that I'm having, it is a good living group. So it can easily leave from the medium. So a positive charge will be formed on this carbon center. Again, here also this OTS group, it can leave and there will be the formation of the positive charge. Among these two, if you see the OMe group that I'm having in the first molecule, this is gonna apply the plus M effect over here. So by applying the plus M effect like this, it will, these electron donations you can see, we can provide the stability to the carbocation which is getting being formed over there, right? So this is stabilizing the carbocation, right? Whereas in the second molecule, if I see this NO2 group that is present, this is gonna apply the minus M effect. That means it is gonna withdraw the electron density from the benzene ring, right? That is gonna create an even positive charge on this particular carbon center. So this minus M effect, it is gonna destabilize your carbocation, destabilize the carbocation. So among the 1 and 2, if I see, 1 is gonna be the species that is gonna give a faster rate for the SN1 reaction in this. Okay, so from the pair X, the first is the correct molecule. So from that you can eliminate the option C and D, where the second molecule they are saying that is gonna give the more faster rate of reaction. So that is not the case, right? Now in the pair Y, if I see there this benzene ring that is present, it can apply the NGP effect for the release of this OTS molecule. So in that, if you see in the molecule third one that I see here, if the NGP effect it is applied, so how many member ring you are getting? So it will be 1, 2 and 3 membered ring it will be formed over here. Whereas in the fourth molecule, if I see the attack, if I do it from the closest position, that is through this particular site, this attack if it is taking place, so how many member ring getting being formed over here? It will be 1, 2, 3 and the fourth one. So comparatively to this one, that is your third 3-membered ring, this less strained ring is getting being formed over here. So fourth one is gonna provide a faster rate for the reaction based upon the ring size that is getting being formed after the attack. You can see if you are doing it from this particular site, even stable ring you will be getting, that is through this carbon center. If I see, I'll be getting is, so this will be 1, 2, 3, 4 and 5 membered ring I'm getting. So that is gonna give the faster rate, right? So that means among 3 and 4, our fourth one will be the one that gives the faster rate of reaction. So first from the pair X and fourth from the pair Y is gonna give us the faster rate. So B is the correct option to this question. Okay. So I hope this one is clear. Let us move up on to the next question now. We have is this one. It says we have to predict the relative stability of the, okay, right. So the relative order of reactivity of the following bromides in the SN1 reaction. So again, the stability of the carbocations you have to compare it. So you can see how many questions have been asked from the carbocation intermediate only. Right, I can see major portion of the organic chemistry questions are coming from your basic portions only, like elimination reactions or your substitution reaction only, right? Or the intermediates, mainly it is your carbocation or the carbene. So basic portion is generally being asked over here. So here firstly let us form the carbocations in this species. The first molecule the carbocation formed will be this one. Here the double bond it will be present and the positive charge it will be formed over here. In the second molecule, after the loss of the Br negative, the positive charge it will be formed over here. And in the third molecule, I will be seeing that this thing is being formed. Here this carbocation species is being formed. So we have to compare the stability of these carbocations only to predict the rate of the reaction. So in the first molecule I can see that this carbocation it will be stabilized due to the resonance. Right. Second molecule if I am seeing the carbocation species that is being formed, it is anti-aromatic in the nature. It is anti-aromatic in the nature because you can see it is cyclic, planar, and it is having the 4 and pi electrons it is present in this. So 4 pi electrons are present, that makes it anti-aromatic. So second one species that is anti-aromatic species is being formed. This is gonna be the least stable one. This is least stable carbocation we are getting. So the least rate of reactivity will be for the second molecule. So if I write the order in this, second one will fall in the last category, right? And in the third molecule if I am seeing, so here this oxygen it contains two lone pair of electrons and these will be present in the p orbitals which are perpendicular to the one another. Only one of the lone pair will be participating in the conjugation with this double bonds that are present. So after that you can see if one lone pair of electrons conjugation we are seeing, so we are getting is a 6 pi electron species over here. That means this particular compound that we are getting, that is the carbocation we have got, this species is aromatic in the nature. So this is gonna have the maximum rate for the reaction since it is maximum stable carbocation formation has been done over here. So the maximum rate will be for the third one, right? And then will be for the first, which is stabilized by the resonance, and the least will be for the second molecule, that is your anti-aromatic species is being formed. So 3, 1 and 2 is the correct option. So that is the option C over here, right? So third one is the maximum followed by the first and least is your second one, right? So this is the answer now. So let us move on to the next question now, that is this one. So here they are saying which of the following compounds would react most readily by the SN2 mechanism. So in the SN2 what we have is, we have this RX species where X is my leaving group. Here the nucleophile it comes. Here is gonna be the sigma star because if this is the sigma bond between this carbon and this X bond, this is gonna be its sigma star. Nucleophile will be attacking from the back side and this RX bond it is gonna leave from the medium, giving us this particular intermediate species. Here this RX bond it is breaking and this R nucleophile bond it is getting be formed over here. This is the transition state that you will be getting, right? Because both these processes are taking place simultaneously. After that we will be seeing that nucleophile and the R bond is formed and this X negative it has left the medium, right? So with the inversion of the configuration you are getting is this particular species getting being formed. So here you can see this attack of the nucleophile when this is taking on this carbon center, there should be it should be less sterically hindered. It should be less sterically hindered one, because for the SN2 reaction we want this order, that is your primary primary alkyl halides or this X group that can be your living group. Primary species that gives the faster rate followed by the secondary and least is for the tertiary centers. And also you can see on the sp3 carbon center whenever we are having the reaction, this nucleophile attack it is gonna take place and not on this sp2 and sp carbon center. We never observe this nucleophilic attack, right? So this scenario we have to observe. So in the first molecule if you see, they are saying that this bromobenzene it is given, the carbon center that is present over here, it is my sp2 carbon center, and on sp2 carbon center we never observe the nucleophilic substitution reactions. So no SN2 reaction you are gonna observe in this case, right? So sp2 they never give this reaction, sp2 they never show this reaction, never show this reaction, right? In the molecule B, if you see, again this carbon center on which this living group it is present, it is again my sp2 center, and on the sp2 center again no nucleophilic reaction you are gonna observe over here. In the molecule C, if I see here this Br negative, if it is leaving, the nucleophile has to attack from the back side. It is very sterically hindered. It is very much sterically hindered one. Sterically hindered species you are having. So here again the attack of the SN2 it will be not possible, because through the mechanism we have seen we want the site to be less hindered for the attack of nucleophile. Again no SN2 reaction you are gonna observe in this case. So the correct answer will be none of the above. In either of the cases you are not gonna observe your SN2 reactions over here. Okay. So D is the correct option for this one. Now let us move upon to the next question, that is this one. This says rank the following alkyl bromides from the most reactive to the least reactive in the solvolysis reaction using the aqueous acetone. Okay, so again the solvolysis, that means the solvent is acting as my nucleophile and the reaction is my SN1. Okay, so here you can see here the living group, that is Br negative. It can be from all of these species that has been given. So we just have to compare the stability of the carbocation that is formed over here. So in the first case, this carbocation species you will be having, here you are having SME group it is present. Here the CME2 and this positive charge it will be formed. In the second case, you will be seeing here is presence of this NH with the C double bond O, and this CH3 species is present. Okay, and here is again this carbocation has been formed over here, right? In the third molecule, there is presence of this NO2 group is present at the para position, and this carbocation is formed over here, right? In the fourth case, it will be this alkyl group it is present like this. So here is your ring, and this is CME2 that is present over here. So in all of this, you just have to compare again the stability of your carbocation. So in the first molecule, I can see this sulfur, it contains the lone pair of electrons and it can apply the plus M effect over here. But this overlap between will be between this carbon atom that is of the 2p orbital and this sulfur atom that is of the 3p orbital. So we are having is a 2p and the 3p overlap over here, which is generally not considered a good overlap, right? In the second molecule, if you see this nitrogen atom, it contains the lone pair of electrons and it can apply the plus M effect, and this is gonna be the maximum stabilized one, because 2p overlap you are gonna observe it, because carbon and nitrogen both are belonging to the second period, right? So this is gonna be stabilizing one. And NO2 group, this is gonna apply the minus M effect over here, so this will be destabilizing our carbocation. So this is gonna be least in the reactivity order, least reactivity in the order, because this is destabilizing my carbocation, so this will be not favored one, right? Here you can see here the hydrogen groups are present, so these can apply the hyperconjugation and the inductive effect over here. So it can apply the plus H or the plus I effect over here. This is also stabilizing my carbocation. So maximum stability I can see it is in the second molecule, that is having the 2p overlap through the plus M effect of the nitrogen group attached over here. So in this you can see only in this options that are given to us, I can observe that this is in the second molecule only. It is given in the option A, that is having the maximum rate for the reaction. So the correct option will be the option A over here, right? So this is gonna be your correct answer to this one. So I hope the reasoning is clear. Also, you can check that through the minus M effect, your third one is at the least one. So that is only in the option A only you are having, and the B also third one was at the last. But here they are saying that first is gonna apply the more amount of the plus M effect, but that is not the scenario because 2p 3p overlap you are observing it over in that case, right? So A is the correct answer to this particular question. Now let us move upon to the next question, that is this one. So we have to predict the major product X and Y that are formed in the given reaction. Okay, so a reaction is given. Here I am having a Br group and this basic medium is given to us, and in the products you can get to know that the elimination reactions are taking place in this. So for the elimination reaction we want the Br group, that is your leaving group, and the hydrogen atom that is on the next carbon center should be in the anti-periplanar position to the one another, right? So we can draw this species in the Sawhorse projection to get the correct product. So the X molecule, firstly I am drawing it into the Sawhorse projection. Here it is, this one, like this. Here is the pH group. The wedge position that is on the right side will be the hydrogen, and here you will be having this methyl group. And here this type of the scenario it is there. Here the pH group is there. At the wedge position you are having is this hydrogen atom, and Br is at the dash position, right? We want this Br group and this hydrogen atom on the other carbon to be anti-periplanar to the one another. So rotations around this carbon centers we have to do it. So I am doing this rotation like this on this carbon center. So this will give me this species. Here the hydrogen atom will be coming at the position of the pH, and here this is at the position of the methyl. The pH group it will come and methyl group will be on this carbon center. And on the second carbon where the Br group it is present, also this rotation is being done. So Br it will come at this particular position, right? And at the position of the hydrogen pH it will come, and here will be the presence of this hydrogen atom. So how is the reaction gonna proceed? So OH molecule has been added. This is gonna come abstract this proton from here. This sigma electron density it will be shifted over here, and this Br negative it is gonna leave from the medium. So alkene is being formed. Now what is the stereochemistry around this that we have to see? So you can see in this case this methyl group that is at the wedge position and this pH group that is present, these both are on the same side. So methyl and the pH are on the same side, and here the other substituent that is this pH and this hydrogen group is present over this side. So this is the molecule that you are getting it, that we can observe in the option B only. I can see B and C it is present, so we have to check the product Y formation as well. So this is for the X molecule you will be observing. Okay, now for the Y also let us have a look. Okay, so just a second. Let me just copy this one and we can draw this molecule. Okay, so this is the one. So now for the Y molecule, let us predict the product. Draw it again in the wedge dash. And this is in the wedge dash form we are having. You can draw it into the Sawhorse. So like this species you will be getting here the pH at the wedge position that is on the right side, methyl is present, and here will be the presence of this hydrogen atom that is at the dash position. On the second carbon center, this pH group I am having. On the wedge side there is presence of this hydrogen atom, and the dash side we are having is this bromine atom, right? So again this hydrogen and this Br has to be brought into the anti-periplanar position, so we can do the rotation around this, and here also this rotation it will be done. So after rotation I'll be getting is this particular molecule. Here the hydrogen it will come over here. Here this pH it will be shifted, and here will be this methyl group it has shifted it. Okay, next is this Br, it will come at this particular position, and here will be this pH group on this side, and this hydrogen atom will be on this carbon center, right? Now this OH molecule it will come, and this is gonna abstract this particular proton from here, this bond's electron density, it will be shifted, and Br negative, it is gonna leave. So this alkene formation, it will be done. This time the pH group, this one and this pH group, they both are on the wedge side. So both will be in the same plane. And here the other substituent, that is my methyl, it will be present over here like this. So this is gonna be the product Y you are gonna observe. In the product X, you were seeing like this alkene was being formed, this methyl group, and this pH were on the one side and this pH was on the other side. This is what you got as the X molecule, right? So now just cross check it with the options that are given to us. So I can see it is in the option B, right? So it is in the option B. You are seeing that X molecule, it is in the trans pH you are having, and in the Y molecule, this pH are on the cis side you are getting it. So the option B is the correct answer to this one. Okay. So now let us move upon to the next question, that is this one. So this question, it says which of the following is true for the reaction that is given to us. Okay, so here we can draw it. This particular molecule it is given in the cyclohexane formation, it is there. We can have it into the chair conformation like this. This is the one. Here the Cl group is at the wedge position, which means it is present in the upward direction like this. On the next carbon center, my methyl group is at the dash, which represents it is at the dash position. And here this species, that is bulky one, it is given at the dash position. So this is the one. This is will be its equatorial position. This is the species that is given to us. So here now this is treated with the NaOMe species. NaOMe species, it has been treated. So elimination will be taking place over here. This is the chlorine group that is gonna leave, and its sigma star, it will be present over here like this. We want the hydrogen atom to be at the anti-periplanar position to it. The carbon center on which this methyl group it is present, on this side the hydrogen atom it will be present, that is not in the anti-periplanar position to this Cl group. So we will be looking upon to this carbon center, and here this hydrogen atom that is present, this is gonna be in the anti-periplanar position to this Cl group. So how is the reaction gonna proceed? NaOMe will be abstracting this proton. This sigma bond's electron density, it will be transferred to the sigma star of this one, and this Cl group it is gonna leave from here. So here you will be seeing the alkene formation, it is taking place like this. Here at this position the alkene is being formed. Here the methyl group is at the dash position, and here this bulky group that was present is also at this particular position. So we can again draw it into the cyclohexane conformation. So alkene has been formed at this position. The methyl group is at the dash position. Here also this substituent it is remaining as it is. So this is the final product that we are gonna observe in this case. So the correct answer, we can see that in the option B and C, we are seeing that this particular alkene has been formed over here. Now we have to predict whether it is my Zaitsev or the Hoffman product. So according to the Zaitsev product, you will be getting is a more substituted alkene. But here we are not getting such type of the reaction conditions that we can get a more substituted alkene. So this is being a less substituted alkene. This is gonna be your Hoffman product over here. Okay, the correct option will be the option C for this one. Okay, so this alkene, how is it being formed? And since it is less substituted one, so we have called it as the Hoffman product. We are getting it. Okay, so let us move upon to the next question now, that is this one. It says which of the following statements are true about the kinetics of the E1 reaction of the alkyl halides in the presence of the base. So E1 reaction. So how does this E1 reaction generally takes place? So you have this RX group like this, you can consider a bulky one like the carbon, this X group is present, and this is the substituted carbon you are having. Firstly, the leaving group, it leaves from the medium like forming a carbocation over here, right? This is the one, and then the elimination it takes place on this carbon center. Suppose one of this R group I am labeling it as to be the methyl group, it is present. So with this there will be the loss of this H positive, and here will be this RR groups and this CH2 species that will be formed over here. So alkene is formed, but firstly the leaving group it leaves, and then the elimination reaction it is taking place over here. So if you see the rate of this particular reaction, this is dependent upon the concentration of the Rx, this R3 carbon, and this X particular molecule only it is dependent, that is your alkyl halide only it is gonna be dependent, and it is not dependent upon the basic medium that we are providing it, because this elimination it will take place in the presence of the base. It is not dependent upon that. The RDS step of this reaction is the formation of this carbocation over here, right? So this is how the reaction is proceeding. Now let us see all of the statements. It says that the rate of the E1 reaction it doubles by doubling the concentration of the alkyl halides, right? So it is true, if you will be double the concentration of this alkyl halide, your rate of reaction it will be also doubled, because your rate is dependent upon the alkyl halides concentration only, right? So the first is the true statement I'm having. Next is the rate of the E1 reaction it doubles with doubling the concentration of base. So is it a true statement? The answer is a no, because the rate for the E1 reaction it is independent of the concentration of the basic medium that we are having. So this one is gonna be your false statement. Next one that we have, it says the rate of the E1 reaction it decreases by changing the alkyl halide from the tertiary bromide to the propyl bromide. So it is again a true statement, because the RDS step of the reaction is the formation of the carbocation. So the stability of the carbocation it matters over here. If we are changing the alkyl halides from the tertiary bromide, that is this one, here the Br, and 3,3 substituent it is having, this is the tertiary bromide. So a tertiary carbocation you will be getting being formed over here to the propyl bromide, which is 1, 2 and 3, and here this Br group it is present. So here the formation of the primary carbocation it will take place. So the reaction is changing. So this is again your true statement. Next one, it says the rate of the E1 reaction it increases by changing the solvent from the DMSO, which is my polar aprotic solvent, to the methanol. So this is your polar protic solvent. This is polar protic, and this one is your polar aprotic. So solvents also plays the role in stabilizing the carbocations. So the rate of reaction again it will be varying, rather it increases if you are changing the from the polar aprotic to polar protic. If you are going, so the rate of reaction again it will increase. So this is again your true statement. So I can see 1, 3 and 4 are my true statement. So the correct answer it becomes the option C over here, which says that the 1, 3 and the 4 are the correct options. Okay, so C is the correct option for this one. So now let us move to the next question that says the IUPAC name of the substrate X and the product Y that has been formed in the following reaction. So a substrate is given. Firstly, you have to write the name for this one. So the species that I'm having is, it looks like this, CH3, here it is CH2, and here I'm having is this Br group. Here is this hydrogen atom, and here this Br, this hydrogen atom, and this methyl group. So numbering we will be starting it from this particular carbon center, because this is gonna give the lowest locant to this substituent, which is my bromide groups that are present. So this is the second carbon, this is gonna be the third, and this is fourth, and this will be the fifth carbon atom. So on the second carbon center we have to firstly find the configuration around this one. So using our CIP rules, we can do that. So at this carbon center, the Br is of the highest priority, being of the highest atomic number, right? Next will be this chain that is going. Third one will be this methyl group, and fourth will be on this carbon center. So if I do the rotation from 1 to 2 to 3, it is going in the anti-clockwise direction, so it should be S, but fourth priority it is on this horizontal line that I am having, so configuration it will be reversed. So at the second carbon center I am having is the R configuration, right? Now on the third carbon center, We have to again check the configuration. So here again you can see Br will get the highest priority, then this chain, and then this ethyl group, and fourth one will be given to this hydrogen atom that is attached to it. So do the rotation 1 to 2 to 3, it is in the clockwise direction, but since again the lowest priority is on the horizontal line, so it will be changed to the S configuration. So 2R and 3S is the correct configuration for this one. So the IUPAC name, it will be 2R3S23 dibromo pentane, it will be there. That we can see in the option A and B we are having is this correct one. The C and D both are saying the RR or the S configuration, so these can be eliminated. Now we have to proceed for the product formation in this. Okay, so the species that has been given to us, it is treated with the sodium iodide in the presence of the acetone. So again the elimination reaction will be taking place where both this Br group, it should be in the anti-periplanar position to the one another. So this is given to us into the Fisher projection. We will be converting it into the Sawhorse. So Sawhorse projection, for this it will be the eclipsed conformation like this. This is the erect Y conformations. This one is the correct conformation from which this Fisher projection has been drawn. So on the lowest carbon center, that is this one, this is the first carbon. Here we are having is this methyl group. On the right side there is presence of this Br, and on the left side is this hydrogen atom. And here on this carbon center, again on the right side is the Br, then this hydrogen, and here is this ethyl group we are having that. Right, now we want this Br group to be in the anti-periplanar position to the one another. So rotations we can do in this on both the carbon centers. Okay, so on the first carbon center, firstly let us do this rotation. Here the Br group, it will come on this carbon center, and hydrogen, it will be shifted over here. Here you will be getting is this methyl substituent. Right, now here we can do firstly this rotation. Here the Br, it will come at this side, the hydrogen, it will be shifted over here, and ethyl will be coming on this position. Now again you can do the 180 degrees rotation in this, just interchange this particular substituent. So you will be getting is this particular species. The Br group, it will be coming on this side, ethyl, it will fall on this side, hydrogen, it will be on this side, and on this carbon center Br, and here is this hydrogen and this methyl species. So this is what the exact conformation of this Br groups we want for the reaction to proceed. Now this is treated with the NaOET. Sorry, this is treated with the sodium iodide. Okay, so this is treated with the sodium iodide. So how is the reaction gonna proceed? So here this sigma star that is present of this particular Br group. So this is basically, I'm not able to draw this. Let me just paste these slides. Just a second. Okay. So this molecule, we will be drawing it over here and seeing the how's the reaction gonna proceed. Okay. So here this molecule we were having, that is your this one. We are having is this Br groups are at this particular positions, right? And here these substituents we just have to draw it now. Here the hydrogen and this methyl group it is present. Okay, and here is this Br and the ethyl, and this hydrogen is present on this particular side. Now the sodium iodide that we have added, so this is gonna be its sigma star now. So this is the sigma star. So this I negative electron density is transferred over here. This electron density it shifts, and this group it leaves from here, resulting into the formation of the alkene species, right? And here you can see this hydrogen atom and this ethyl group. These both are on the wedge side. So here you will be getting this hydrogen and this ethyl is on the same side, and this methyl group and the hydrogen atom it is present on the same side. So what type of the alkene you can see we are getting is, it is both the higher priority groups, this is 1 and 1, they are on the opposite side you are having. So E alkene you are getting it over here, right? So the correct option it will be the option A over here. You can see E pen to ene is getting being formed after the reaction. So A is the correct option for this particular question. Okay, so this is gonna be the correct answer to this one, right? So now let us move upon to our next question, that is this one. So again a reaction has been given to us, we have to predict the product in this case. Okay, so in this substrate you can see the CO2 Me group is there, that is an electron withdrawing group we are having, right? So these protons that are present on the carbon that is adjacent to it, it will be acidic in the nature, and in the reaction medium you can see firstly is the methyl oxide has been passed over here. So this methyl oxide it is gonna abstract this particular proton from this particular carbon center. So this species you will be getting it over here, that is this one. Here the carbonyl species that is present, and here this I'm opening this ester group that is given to us. So now the negative charge has been formed on this carbon center, which is stabilized due to the resonance. That is why I said that this electron withdrawing group it will be stabilizing this particular carbon center. So after that we will be getting is this particular species formed over here. Here this carbonyl group it is remaining as it is, and you have got us. Okay, so we are having this alkene group formed over here, and here will be this O negative and this OMe group it will be present at this position. Right now you can see this O negative it can provide a push to this pi electron density will be shifted, and this O negative it can be opened from here. So this opening reaction it is basically of the lactone, it is basically taking place over here. So you are getting is this species. Here the C double bond do, and here this O negative will be formed, that after the protonation will be converted into the acids, right? So we will be getting is here this alkene it will be formed, here the double bond it will be present, and here will be this C double bond O and this OMe group it is present as it is. So you have to check the conformation around these double bonds. So here you can see initially the species that we were having, here it was, you can check it, that the CO2 Me group it is present in the above side. So in the final product also it will be present in the above conformation only, and around this double bond also, this that is in the ring, it is in the cis conformation we are having. So in the final product also this is gonna be in the cis conformation only. So this is the exact conformation that you have to check in your products. Okay, so here in the option A, they have changed the configuration around this double bond which was present in the ring. So this is not gonna be your answer. In the option B, again you can see that this conformation around this double bond, they have changed it. They have made it anti position. So that is again not gonna be there. In the option C, if I check, this is in the cis conformation, right? Around this double bond, now this CO2 Me group, they have brought it into the anti position, because this bond and this bond you can see they are at the anti position. So again this is not the scenario, because we are seeing that in the final product both of these bonds that are in the same conformation I'm getting it, that is in the cis conformation. So D is gonna be the correct answer to this one, where around this double bond both these are in the cis conformation, and around this double bond also both are in the same conformation we are having it. So D is the correct answer for this particular question. Okay, I hope this one is clear to you. Now let us move upon to the next question, that is this one. So again we have to predict the major product formed in the given reaction sequence. So in this particular species, the substrate given to us is like this. Here the alkene group it is present, here this, and this four membered ring it is present, and this is present over here. Now this is treated with the bromine water, for it is treated with that. So how is the reaction gonna proceed? This alkene electron density that I am having, this will be transferred to the sigma star of this Br bond that you are having. So it will result into the breaking of this sigma bond. So first species that is formed over here will be the brominium ion is formed in this case. So here you will be having this bromine with the positive charge, and here the rest of the substituents are remaining as it is. Right? So here this species is present. So you can assume that this brominium ion, it is formed in the wedge conformation. That is from the upward plane. Either you can consider it into the upward plane or the downward plane. Why we are taking it? Because stereochemistry has been asked to us in the final products. Okay, so this is with the bromine treatment you are going to get. Now in the next step they have added the water to it. So water will be attacking on the site which is your more substituted one. That is at this particular site it will be attacking, and this bond it will be opening. Since now Br group it is present, brominium ion it is present in the wedge conformation, the water that is its OH group it will be coming from the dash position to it now. So we will be getting is this species. Here the four membered ring it is remaining as it is. This one is as it is. At this position at the wedge the Br group it will be present. Now at the dash position the OH group it is coming, and the methyl group it will shift onto the wedge position to this one. So this is after the first step the species that we are gonna get it. Right. Now in the next step they have treated it with the H2SO4 and the heating has been done. That means here the acidic medium has been provided. So with that what is going to happen, this oxygen molecule that is containing the lone pair of electrons it will be protonated, right? So this will be now protonated. So we will be getting here the formation of the water at this site. So at the wedge position Br it was present, here at the wedge position the methyl group, here at the dash position now the water group it is formed at this site, right? So here this bonds are remaining as it is. Now water it is your good living group, so it will be leaving it because heating conditions have been given, so it can easily leave from the medium. So we will be getting here the formation of the carbocation, right? Here the Br group it is present. Now here since the carbocation will be formed, so it becomes the planar species now. Methyl group it is present over here. This species it is present like this. Now in the next step, what is gonna happen? This hydrogen atom, because heating condition has been given, elimination is possible over here. This H positive it will be lost and this alkene it will be formed. We will be forming a more substituted alkene. That is why this alpha position hydrogen we have left it, and not this methyl group alpha position we have left it, because this will form a less substituted alkene. We want the major product to be formed, so this will be the one. So the final product you will be getting here the alkene formation. Here the Br group it is present as it is, and here there will be the methyl group presence. This four membered ring as it is, and this double bond, this two of the alkyl groups are remaining as it is. So this is gonna be the final product, so that I can see in the option B I am having it. So this is gonna be the correct answer to this particular question. Okay. So now let us move upon to the next question, that is this one. So we have to predict the precursor, that is the starting material you have to predict X, that is the name that is given to it, that is gonna form this particular product. So a species have been given to us. We have to predict which is gonna form this particular product. Okay, so treatment has been done with the NaOMe and this water conditions have been given. Water is passed to it. So how is the reaction going to proceed? In this, if you see in all the molecules that are given to us, we are having a diketo species. That means two of the ketone species are present, and in between them, this hydrogen centers that are present, they are acidic in the nature. If I treat them with the this NaOMe, this will abstract the proton from here, resulting into the formation of the carbon ions on all these centers, right? So in the first molecule that is given, the carbon ion that we will be getting will be looking like this, the enolate species. Basically it will be formed over here, this one. Here the ring has been formed over here, and here this ketone is present. This is alpha beta unsaturated. So if I form the enolate over here, that is this resonance structure, I can draw it. So after that we will be getting, I'm just directly drawing it over here only. So here this alkene it will be formed, and here this O negative will be formed over here. You can form it on either of these sides, but through the ketone they are more acidic, so that is why I have drawn it on this particular side. In the next step you can see, now this carbon center, this electron density from the oxygen it is shifting, and this carbon center that is becoming nucleophilic, it is soft in the nature, right? Because it is your resonance stabilized one. So charge has been dispersed in this case. So this carbon center is the soft one. This can attack over this species, that is your alpha beta unsaturated, where this fourth carbon center, because this is 1, 2, 3 and the fourth center that you have is your soft in the nature. So according to the HSAAB principle, that is your hard soft acid base concept, if you see it, HSAB principle, the soft side they interact with the soft centers only. So this electron density it will be attacking over here. This electron density it can be shifted like this. So the soft is attacking over the soft side. So after the attack I am seeing that here it will be the bridged system, it will be formed over here like this. This ring it is remaining as it is. This electron densities we have shifted it, right? And here this ketone species it will be present, and this carbon center that is present, it has attacked over this particular site, which is further attached with this OME group it is present over here. So something bridged system I am getting. I am not getting the desired species formed over here, because in the final product I want is this particular 5-membered fused system it should be formed. But it is not getting being formed in this particular case. So that means A is not the correct option for this one. Let us check it for the other option now, that is for the B1. In the similar manner the reaction we are gonna see. So this proton they are acidic, so here will be the anionic species or the enolate it will be formed over here, right? So let us just draw this one over me. Second one I am drawing it. Okay, so here this negative charge it will be formed. So here is this ketone species. Okay, now next is the species that is present. So here the carbonyl species that is present now. So in this case, if I am seeing the enolate, you can form it directly like this. Here will be this O negative and here will be this double bond, right? So again this is your soft center now. So this electron densities that will be shifted. This can attack on this particular carbon center, and this electron density it will be shifted. So after this particular reaction you will be seeing that you will be getting is a fused system. So how many membered ring we are getting? 1, 2, 3, and this is, I guess I have missed one of the carbon center, so it will be 5 carbon atom species you will be getting it formed over here. Here this carbon atom I missed it, so here you will be getting a 5-membered ring formed. So this is second, third, fourth and the fifth one. So a 5-membered fused ring it will be formed over here. So you will be getting is this 6-membered ring. Here the O negative it has formed, this bond it has shifted. So here on this carbon center, one this double bond it is, this CH2 it is present. On the next carbon center this ketone it will be present, right? And this carbon center that was present it has attacked over this particular site, and to this particular carbon center CO2 Me group as it is attached over here. So you can see something that is desired in the product formation, it is we are getting close to it. So you can convert this enolate now in the resonance we can do in this, and this enolate it can be converted into the ketone species like this. So this is the final product that we are getting in this particular B molecule, and this is what you can see in the desired product also it is getting being formed over here. That means it is through the path B, that is if the starting material is B and you treat it with the NaOMe and you treat it with the water, you are gonna get as your desired product. Okay, so the C and D also you can check your answers whether you are getting it or not. So you will be not getting in that cases obviously, because this is the desired answer. Okay, so B is the correct option for this one. Okay, Now let us move upon to the next question, that is this one. It says the major product of the following sequence we have to predict. So this is the species that has been given to us. Here the alkene it is present, at the wedge position this methyl group it is present. This is treated with the Hg OAC whole twice. That is, and along with that the methanol species have been passed over here. So how is the reaction gonna proceed? This alkene species and this mercuration, basically it is gonna take place over here. So at the wedge position already this methyl group is present, so the upcoming Hg species that is present, it will come from the dash side. So here there will be the positive charge, it will be present over here. So this species we will be getting. Now in the next step, along with this they have passed is the methanol over here. So methanol now it can attack on to this carbon center, also it can attack on this particular carbon center. Both the sides the attack is possible, so resulting into the formation of this particular species. At the wedge position this methyl group it is present. Now this at this mercury group that is present, it is at the dash position, so the methanol it will be attacking from the wedge position. So this species we will be getting, that is here at the dash position. You can say this is Hg species that we have got it, which on further treatment with the NaBH4 and the methanol that is acting as a solvent, demercuration it will be done, and here we'll be getting as this species as the final product. Here the OMe it will be present. Similarly on this other case also you will be getting is the attack we have done it. So at this particular position, at the wedge position, this OMe group it will be present, and at the wedge position, this methyl group was present. So these are the two of the products that you are gonna get in this particular cases. Okay. So the answers you can check it from the stereochemistry, that is through the option A. We can see that both of the substituents are at the wedge position at the 1,2 and at the 1,3 position we are getting it. So A is the correct option for this one. So now let us discuss about the next question, that is this one. So we have to predict the major product in the following reaction sequence. So the species is given to us. Again the alkene is given and it is treated with the mercury species. So again mercurinium ion you can say it is being formed. So this species it will be formed after the attack. 1 2 3 4 1 2 3 4, and here this, here the at the double bond position this Hg, and this will carry the 2 positive charge over here, right? Now the intramolecular attack is possible. You can see this oxygen molecule that contains the lone pair, it can intramolecularly attack over this side, and this bond it can open from here. So how many ring formation it is taking place over here? So it is 1 2 3 4 5, and this is the sixth carbon, sixth atom that is present. So six membered ring it is getting being formed over here. So we are getting as this ring. At the one of the position the oxygen atom it is also present, right? So you can do the numbering for this. So this is 1 2 3 4 5 and the sixth one. At the first carbon center there is one methyl group that is present like this, and the other species is this, again this methyl substituent it will be present, and this Hg positive it will be present as the substituent, right? So that after the mercuration it will be demercuration, it will be removed from here. So this is gonna be the final product you are gonna get as the answer, a 6 membered ring with 2 of the methyl substituent, that is exactly like this one. This is your 6 membered ring. At this position the oxygen atom it is present and 2 methyl substituents are present over here. So I can see 6 membered ring is formed only in the option A. In this option here the oxygen atom it will be also present, that by mistake the printing mistake has been done over here. So the correct option will be the option A. You can insert this oxygen atom over here, right? Because this 7 membered ring it will be not formed, because this oxygen atom intramolecular attack it will be at the more substituted carbon center it will be taking place, and not on this less substituted carbon center. This has been formed when the less substituted carbon center attack has been done. Okay, so this is gonna be the correct answer. Now let us move upon to the next one, that is this. Which of the following compounds do not serve as a Michael acceptor? So what is Michael acceptor? Basically for the 1,4 addition, the species that you have, that is your 1,4 this alpha beta unsaturated species. This is your Michael acceptor. This is your Michael acceptor. Right, one for the 1,4 addition you have to see this. Now among this you can see this, I am having the alpha beta unsaturated, so this can act as my Michael acceptor. Next, if you see in the molecule B, if I see, so this carbonyl species, it should be adjacent to the carbonyl species at the alpha beta position, there should be double bond. Here this oxygen atom, it is present, and to this position this double bond it is present. So in this case this is not gonna behave as the Michael acceptor. This is the structure that you want, that is alpha beta unsaturated carbonyl species. So B is the correct option, that it is not gonna behave as my Michael acceptor. You can check for option C and D as well. So carbonyl species is present, alpha and beta position to it, we are having the double bond present, so alpha beta unsaturated carbonyl compound is there, so it can behave as a Michael acceptor. Option D as well, you can see this is the alpha and this is the beta, again it can behave as my Michael acceptor, but the B is not the Michael acceptor, so B is the correct answer to this one. Okay, so now let us move upon to the next question, that is this. So final product formed in the following reaction sequence. A reaction has been given, we are having a pentadiene system like this, it is given to us, and this is treated with this particular species. This is carbonyl and this OMe. Heating condition has been given to us, so 4 plus 2 cycloaddition reaction it is gonna take place in this, right? So how is the reaction gonna take place? So this reaction, this electron densities are shifted like this, giving us this particular species. Here the double bond it will be formed, this 5-membered ring it is as it is, and this bond has been formed over here, right? Now at this particular position CO2 OMe group it is present. So this is the species that I am having, so we can present it into the chair conformation like this. Species will be formed, this bridged position, this carbon center will be present, this is the double bond it is present. Now this CO2 Me group that is present, that can be placed in the endo and the exo position. Endo means in the downward direction and exo means in the above direction. So it will be in the endo conformation we are gonna have it, because the carbonyl species that is present in the COMe, it can show the secondary interaction with this alkene group that is present, right? So the endo species it should be formed over here, right? Endo species it will be formed, right? Now in the next step what they have done is, so this species we are getting so far, this is the one, and this double bond it is present, symmetrical environment it is there, either your CO2 Me can be placed at this center or on this carbon center, it does not matter, so I'm placing it on this particular side. Now in the next step they have treated it with the osmium tetraoxide, this is the one, osmium tetraoxide, then with this NaHSO3, and the water condition has been passed over here. So this is responsible for the formation of the diol species. So this forms our diol species, this alkene group it will break and the diols will be formed over here. Now this, with this osmium tetraoxide, this is gonna react on the less hindered site, less hindered site it will be attacking. So we can see on this alkene species, the above side that is present, it is free for the attack, because only one carbon center hindrance we are observing in this case. Rather in the bottom direction, the cavity that you are having, two carbon centers hindrance you will be observing. These two carbon centers will provide the hindrance, so that is not gonna give you the favored reaction. So that means the diol species that will be formed in this case will have this particular stereochemistry. Here it will be present in the above conformation. The CO2 Me group it will be present in the downward direction. So this is gonna be your final product. That is one that is in the endo conformation, along with that the less sterically hindered one. Less sterically hindered attack we have observed it, right? So the correct answer you can match it. So this is given in the exo conformation, this is also in the exo, so these are not the answers. This is in the endo conformation and this one is also in the endo. Here the OH groups are drawn in the downward direction. So this is not the correct answer because you can see lot of hindrance you are getting. So D is the correct answer for this. Okay. Now let us move upon to the next question, that is this one. And it says that an unknown compound with the molecular formula C10H14, it decolorizes the bromine in the presence of CCl4. That means unsaturation it is there, and due to that this decolorization it is arising. When it is titrated with the warm concentrated KMNO4, the compound, it gives us the 6-cis cyclo. This is cyclohexane 1,2-dicarboxylic acid, and the oxalic acid is getting being formed. What is the structure of this particular product? Okay, so in all of the given molecules you can see there is presence of the unsaturation. That means all of them they will be decolorizing the bromine solution. Right now when you are treating them with the carboxylic, this KMNO4 solution, you have to predict the final products in this cases. Right. Now on treatment with the KMNO4. Now KMNO4 species that we have, it is my strong oxidizing agent, right? So it will be giving us the acid species, right? So in this, if you observe the molecule C that is given to us here, this is the species like this. We want it into the, since it is given cis conformation we want it, so you can directly eliminate the option A and B, because here the hydrogen atoms they are in the trans conformation, so trans decalin type of the system it is given, so this is not gonna give you the correct answer. This will be forming the cis conformation because cis decalin is given to us. So in this, the cis conformation in the option C that is given to us, this is the one. Here this diene species that is present. If you treat it with the KMNO4, on treatment with the KMNO4, what you will be doing is this double bonds they will be breaking, and at this position the acid groups it will be formed. So you will be seeing this species you are getting here, this the hydrogen groups they are in the dash position you are getting, and at the double bond position you are getting is the formation of this acids over here. So this double bonds have to be broken and this acids will be formed, and along with that around this double bond also, that is on the other carbon center, that is that due to this carbon centers you will be seeing there will be the formation of this acids over here. So this will be converted into the acids, so COOH, and along with that the other COOH species that will be. So this is the molecules that you are getting. So here you can see we have got is, one is we wanted was cis cyclohexane 1,2-dicarboxylic acid. Here both of this OH COOH groups they are present in the same conformation, because if hydrogen is at the dash, this will be at the wedge positions you will be getting. So you have got your cyclohexane 1,2-dicarboxylic acid, dicarboxylic acid, and here you have got it. This is known as your oxalic acid. That means through the option C, if I check it, where the double bonds are in the adjacent positions, I can get the oxalic acid formation. If you will be going through the path number option D, if you are seeing, so here this bond it will be breaking and this bond you will be breaking, so rings will be not formed in that case. So cyclohexane possibility it will be not there, so that is why the option is C over here. So I hope you are clear that why this option, other options have been eliminated. A and B on the basis that this is gonna give you the trans conformation, and the D option is eliminated because the cyclohexane formation you are not gonna get in this case. So the correct answer it becomes our option C in this case. Okay. So now let us move upon to the next question, that is this one. The major product of the following reaction we have to predict it. So a decalin system has been given to us. Firstly, draw it into the chair conformation. Since it is the trans-decalin, we can draw it in this particular form. The methyl group is in the above direction like this, and the hydrogen is present in the downward direction, and here I am getting is this alkene formation, right? This is treated with the bromine atom. bromine molecule it has been treated. So in the wedge conformation, that is in the upward direction, you can see there is the presence of this methyl group which is gonna cause the hindrance. So that means this alkene species, it will be reacting with this bromine molecule that is from the downward direction, and this Br negative it is gonna leave. So this particular species that will be formed in this cases like this. Here in the above direction the methyl group, in the downward direction is this hydrogen. Now this in the downward direction the Br group it will be attaching, forming the brominium ion, right? Now in the next step again, the water molecule that is present, it will be coming for the attack now. So you can see now at this particular site, this axial site it is vacant, and here is this is the axial, and this is in the downward direction the equatorial side, and in this particular case its downward direction, since the attack has taken place, so its axial side it is blocked over here, right? And this equatorial side it is vacant, this one is just vacant for the attack. So the water molecule it will be preferably attacking from the axial side, so this side it will be attacking, and this brominium side it will be opening from here. So we will be getting is this particular species, because axial attacks of the nucleophile we generally observe it. So this is the methyl group, and this is the hydrogen. So here the OH group it will be coming from the above direction, and Br it will be shifting in the downward direction. So this is the molecule we are getting. Now in the cyclohexane conformation we can draw it like this. Here at the wedge this methyl group was present, at the dash there is this hydrogen atom. Now this OH group it is present in the above direction, which shows it is on the wedge conformation. I am getting it, right? And the Br group that is present, it is in the downward direction, so it will be at the dash conformation. So this is gonna be the final product. You can match it with the options now. So we can see that this is your option D you are getting. So here the OH group it is at the wedge position, and Br is at the dash position. I hope the mechanism is clear in this question. Okay. So now let us move upon to the next question, that is this one. This question it says, which of the following is the most stable intermediate in the following pair X and Y respectively? Okay, so pairs have been given. You have to predict the stability of again the carbocations. In the pair X, if I see this OH group that is present, it can apply the plus M effect over here like this. It will be stabilizing the carbocation over here. This is applying the plus M effect, and in this particular case I cannot see this methyl group that is present. It can apply the plus H or the plus I effect only it can apply, and the magnitude of the plus M effect it is more as compared to the hyperconjugation and inductive. So in the pair X, our first molecule it is gonna be more stabilized one. Right, now let us see in the pair Y, this NO2 molecule that is present, it is your electron withdrawing group. It can apply the minus M effect. So I can see in this third molecule that I am having, so this electron density it can be shifted like this. So this is resonance, it is possible in this. So this is gonna apply the minus M effect, and this will be this carbon ion, due to that it will be stabilized one. Whereas in the second, that is in the fourth molecule that is given to us, I cannot see there is this mesomeric minus M effect is not applicable in this particular case. So among 3 and 4, your third one is gonna be more stable one. So 1 and 3 are the correct options, that is according to their stability. So option A is the correct one for this one. Okay. Now let us move upon to the next question, that is this. It says the major product X and Y that are formed in the following reaction sequence. So two of the reactions have been given to us. We have to predict the products in this. So the first species that is given to us is like this. Here the Cl group it is present, and here I am having is this N, H, and this methyl group it is present over here. Right. Now this is treated with the K, N, and this is C2H5 whole twice it is given. So K positive, basically a basic medium has been provided in this case. So this is H, N, and C2H5 it is attached over here, right? So now how is the reaction gonna proceed in this case? You can see this negatively charged, it can abstract the proton from here. This negative charge, it will be formed over this nitrogen center, which will be stabilized due to its electronegativity. So we will be getting is this particular species. Here the Cl group it is as it is. Here this electron densities, and here will be this negative charge and this methyl group. Now this becomes the ready intramolecular nucleophilic attack it can give on this particular center, and this Cl group it can leave from here. So resulting into the formation of a ring type of the structure that will be of the 1, 2, 3, 4 and the 5 membered ring it is getting being formed in this particular case, right? So species I'm gonna get here is this 5 membered ring with this nitrogen atom present at this particular site, and this nitrogen is attached with this methyl substituent. So this is the product that I'm gonna get in the molecule X when I am doing the reaction. Okay, so this is the molecule X over here. Now for the Y molecule also, let us see what is gonna be the product formation. So let us just copy this one. Okay, so this is the molecule that we are having. So now let us draw the reaction in this. Okay, so the species that has been given to us is this ring we are having. Okay, and here is this Cl molecule that is present, and here this double bonds are present like this. Here the N, Ne and this hydrogen. And this case you can see it is K, N. Again that same species has been passed in this case. So this time what is gonna happen? You will be seeing this proton that is present over here, it can be abstracted, and this electron density it will be shifted, resulting into the formation of the benzene species over here. You will be getting is, in the previous case the direct attack it was possible, so direct attack it has been done and not through the benzene mechanism we have gone it. Here the benzene mechanism it will be going through that. Okay, so this is the species we have got it. So 1, 2 and this nitrogen with this methyl group and this hydrogen atom it is present. Now in the next step you can see this nitrogen it contains the lone pair of electrons. It can attack over here. This electron density it will be shifted over here. So you will be getting is this particular molecule. Again the 5 membered ring it is getting being formed in this particular case. So work up along with this only we have done it. So final product is this one. So this is gonna be the molecule Y that we are gonna observe. So the mechanism in both of the cases is the different. One is through the direct and other is through the benzene mechanism you are observing. So the product formed is same in both the cases. That is the option D we will be getting in this cases. Okay. So this is gonna be the answer to this question. Now let us move upon to the next question, that is this one. So again the reaction has been given to us. We have to predict the major product in this. So the species that has been given to us is like this. Here the fluorine it is present. Here the CN group, and this is the Cl group. So you can see at the ortho and the para position to this fluorine group. This is its ortho position, and this one is at the para position, the Cl group it is present. Both of this they are my electron withdrawing groups. These are my electron withdrawing groups. So whenever the electron withdrawing groups at the ortho and the para positions are present, nucleophilic attack is possible. Nucleophilic substitution reactions you can observe in these cases. In these cases, this ammonia molecule will be behaving as a nucleophile, and you can see the negative charge is coming after the attack. If you are doing it on this side, after that the negative charge is coming at the ortho position, where the CN group that is present it will be stabilizing the charge like this. Here this fluorine group it is present, and this NH3 that we are taking, that proton has been lost from here, and NH2 it is present, and here this negative charge it will be present. So cyanide group it is present over here, and the other double bonds that is present like this. Also you can see further resonance you are doing it in this cases. So Cl group will be also again stabilizing it. That means this nucleophilic substitution reaction, it is possible in this, because generally in the case of benzene we see the electrophilic substitution. Already there is presence of the pi electron density, so nucleophilic attack it is not possible. But whenever at the ortho or at the para position we are having the electron withdrawing groups, so in that cases the this nucleophilic substitution it is possible. So here it is nucleophilic substitution reaction that is taking place in this cases. Okay, so the negative charge is stabilized over here. Now further the elimination. So firstly addition is taking place and then the elimination will be taking place. Now the negative charge again it will be coming and the fluorine group it is gonna leave from here. So final product you will be getting is like this one. Here the double bonds it will be present, and here at this position instead of the fluorine now this NH2 group, and here this cyanide group and this Cl group it will be present over here. So this is gonna be the final product. Now from the options you can match it. So in the B, C and D you can see there is still the presence of the fluorine atom it is there. So that is not the correct answer. The correct answer it becomes the option A over here. Right, because at to this fluorine group at the ortho or at the para position the negative charge it was being stabilized. So we have done is addition and then the elimination. Then elimination has been done in this case. Elimination. Okay. So that is it. Now next question that you have it is this one. Arrange the following alkyl benzene in the increasing order of the percentage of the ortho-para ratio products formed in the nitration. So different molecules have been given to us. We have to predict the products in which the major ortho product has been formed, because ortho to the para ratio is being asked. So we have to predict the one in which the ortho product is formed in the major amount as compared to the para position. So the given molecules, their names have been given to us. Firstly, we should be able to draw the structures of this. Toluene. First is this one, the benzene ring. To that this methyl group it is attached. This is called as the toluene. Next is the cumene. In the cumene, there is presence of the isopropyl benzene. That is this one. So 1, 2 and 3 carbon atoms in the isopropyl benzene, that is called as my cumene species. Right. Next is your tertiary butyl benzene, which is like this. It is now further substituted, so that means the carbon center it is tertiary. This one, this is tertiary butyl. This one. Okay, so this is my tertiary butyl benzene. Right. Next is we are having ethyl benzene. Right. This is the one. So CH2, CH3. This is the one. So this is my ethyl benzene. So all of these molecules that is given to us, these are my alkyl substituents are attached to the benzene ring, and all of this they are capable of applying the inductive effect or the hyperconjugation effect. They are able to apply to the benzene ring, making them to be the ortho para directing in the nature. So we can say that all are ortho and the para directing in the nature, right? Ortho para directing. But how is the ratio gonna be defined over there? So you can see as we are moving from the toluene to the cumene then to the tertiary butyl benzene, the hindrance of this particular substituents that are attached over here, they are increasing. So due to that, what is gonna happen? The attack at this ortho particle or this, if the nitration you are doing at the ortho position, the attack it becomes less to a lesser extent it will be taking place, because this tertiary butyl group you can see this is very large group, so it will create lot of hindrance. So the preferential attack in this particular case it will be at the para position. That means its ortho amount it will be lesser one. We want the one species in which the ortho product to be the major one. So that will be in the case, that is in the molecule in which there is least hindrance of this substituent it is present, that is in the toluene you are observing. So we will be observing that the least hindrance it will be in the case of toluene. So ortho product it will be formed at that particular in this particular molecule, followed by your ethyl benzene. That is, as compared to the methyl, this one is the next bulky molecule we can observe. Next we will be having, it is in the cumene, which contains the isopropyl benzene. So again a bit hindrance, it is more as compared to the ethyl substituent, and least will be in the case of the tertiary butyl benzene, that is the most hindered one. So in this case the ortho-para product ratio that we are gonna get, it will be the least one, right? So the correct answer is this, that is options you can match it. This becomes the option number 1. Ethyl benzene is the fourth one, cumene is at the third one, and the cumene is at the second one, and this tertiary butyl benzene, this is in the option third one. So 1, 4, 2 and 3, this is gonna be the correct answer to this one. So the correct answer, it becomes the option B in this case. Okay. Now let us move upon to the next molecule, the next question, sorry, that is this one. Which of the following substrate do not participate in the Friedel-Crafts alkylation? So in the Friedel-Crafts alkylation, how does the reaction set proceed? So you get is a formation of the carbocations over there. So because this species AnCl3 generally you have it, and you treat it with this RBr, suppose you are having. So here, how is the reaction going to proceed? This is my Lewis acid. Lewis acid. This will form the AnCl3, and this Br group, it will be present. Overall negative charge it will be forming, and R positive species it is being formed. So this is what this RBr species have been given to us. So in this cases you can see carbocation formation it takes place, that further goes for the attack over the benzene ring. Right, so we have to again compare the stability of the carbocations only, in which of the molecules the carbocation formation is not taking place, or it is least stable one, that is not going to participate in the Friedel-Crafts alkylation. In the molecule A, if I see leaving this Br negative from the over here, the carbocation is getting being formed over the sp2 carbon. So on the electronegative species, because sp2 percentage S character it is high, so it is electronegative. At the electronegative, a positive charge it is coming, that is not gonna be favored one. So at this particular site, no carbocation formation it will be taking place. So I guess this is gonna be the correct answer, because here the no carbocation formation and it will be taking place. You can check it into the other options as well. In the molecule B that is present, here this benzylic carbocation it is getting being formed, so the reaction can proceed. In the C molecule, if I see here on the carbon center, that is your sp3 carbon center, positive charge it is coming, so again it can proceed for the reaction. In the molecule D, if I see here this allylic carbocation it is getting being formed, so again it is on the sp, this is in the high resonance it will be there, but this still can participate in the reaction. So this is directly on the sp2 carbon center only, no rearrangement. So A is the correct option, that is not gonna participate for the Friedel-Crafts alkylation reaction. Okay, so A is the correct option. Now let us discuss about the next question, that is this one. Which of the following statements is not true about the reactivity towards the aromatic nucleophilic substitution reactions? Okay, so first statement it says that 2-chloropyridine it is more reactive than the chlorobenzene. Okay, so the species that is given to us, it is my 2-chloropyridine. At this position, this chlorine group it is present. So this is the species that is given. Okay, so we can show the resonance in the other form also, like this. Here the double bonds presence we can show, and the other species they are saying it is your chlorobenzene. Okay, and this is the chlorobenzene. So this benzene ring just I am having, and this chlorine species, and the nucleophilic attack they are saying it is taking place. So nucleophile, if it is attacking on this particular site, so here you can see the electron density when it is shifting. Here the negative charge it will be coming onto the nitrogen center, right? Here the Cl and the nucleophile has attacked over here. Negative charge is coming after the attack over the nitrogen center. Whereas in the chlorobenzene, if I do the attack, the nucleophile it will be coming. It is attacking over here. The electron density that is coming is on the carbon center. You can see this species you are getting Cl nucleophile and this double bonds. So this negative charge is formed over the carbon center. We know that the electronegativity of the nitrogen, it is more than that of the carbon center. Alright. So that means the negative charge in the 2-chloropyridine case, it will be more stable one. So this is more stable. So the reaction, it is feasible in this particular case and not in the case of the chlorobenzene. So it is the correct statement that says that 2-chloropyridine, it is more reactive than the chlorobenzene. Reasoning you have seen it, right? Because negative charge is getting being formed over to the nitrogen center. So in this case, the reaction, it will be feasible, right? In the next statement, they have said, they are saying that the idobenzene, it is more reactive than the fluorobenzene. So this is not the correct option. You can see. Just a second. Okay, so next is they are saying that the idobenzene. Next they are saying is that my idobenzene, it is more reactive. So idobenzene is basically this one. This species I am having, right? And the fluorobenzene, this is the one, the species I am having it. So they are saying the nucleophilic attack over the idobenzene, it is more stabilized. You can see if nucleophile attack, I observe it in this case. Suppose it is attacking over this side, the negative charge which will be coming on this particular iodine center, it will be coming. Whereas in this case, the nucleophile attack, if I am doing it on this carbon center, this will be negative charge, it will be coming on this particular side. So you can see if the nucleophile has attacked on this side, here the idobenzene, and this is the negative charge, and this nucleophile attack over here, and the fluorine species that is present. So this is the negative charge coming at this particular site. This one is more stable one. This reason for that, it lies in the fact that my fluorine is more electronegative as compared to the iodine. So this is not gonna be the correct statement, which according to them, they are saying that my idobenzene, it is more reactive, but rather fluorobenzene, it is more reactive. So this is gonna be the false statement in this case. So we want to find the incorrect statement only. So B is the correct option. Generally you observe this case that fluorine, bromine, and then the iodine. This is the correct order for the nucleophilic substitution reactions in case of the this halobenzene when you are having it. Okay. Next statement also you can check that 2-chloronitrobenzene, it is more reactive than the 3-chloronitrobenzene. So this is the molecule. We are having 2-chloronitrobenzene. So Cl, and this is the nitro, and the other case it is 3-chloronitrobenzene. That means this one. At the third position, the NO2 group it is coming. Here the nucleophilic attack, if you will be seeing in this case, if the nucleophile it is attacking on this particular carbon center, the electron density, it will be stabilized due to this NO2 group. Whereas in this case, if you will be seeing the nucleophilic attack, if you are doing it at this particular carbon center, this electron density, it will be not stabilized. So this is again your true statement only. Okay. Next is 2-chloropyridine. It is more reactive as compared to the 3-chloropyridine. Again, you can do it confirmation through the structures of it. So the correct option we have got is the option B in this case. Now let us move upon to the next question, that is this one. It says which of the following is the correct sequence for the preparation of the ethyl 2,4-dinitrophenyl ether. So what we wanted is the species ethyl 2,4-dinitrophenyl ether. So this is the molecule C2H5 you are having, and at the second and at the fourth position the nitro group it is present. This is the exact molecule that we want, that is ethyl 2,4-dinitrophenyl ether. This molecule synthesis we have to do. So through the path number A, if we are following, so what species you are getting? This is the benzene ring I am having. Here the in the HNO3 and the H2SO4, this will do the nitration of this particular molecule. So we will be getting is this species NO2 group, it will be present. Next is the Br2 with the FeBr3. FeBr3. This is gonna do the bromination of this, and NO2 group, it is your electron withdrawing group, that is your meta directing species. So you will be getting here the bromine species, you will be getting it over here. So this is something you are getting it. Further treatment has been done with the NaOET. So this can substitute your Br group. So here at this position the OET group it will be coming, and here this NO2 group it will be formed. So this is not the desired product we are getting, right? So this is not the correct answer. Through the path number B, if you are following, so you will be seeing that the reaction is, this is the benzene ring. Firstly, it has been treated with the chlorine in the presence of FeCl3. So chlorination is basically being done over here. So you will be getting here the chlorobenzene formation, and then you do the nitration of this HNO3 with the H2SO4. So chlorine atoms, though it is your electron withdrawing, but it is your ortho-para directing in the nature. So we will be getting this particular species here, the chlorine, at the ortho position as well as at the para position. The substitution will be done in this case. Next is treatment is done with the NaOET. So now again the NaOET, it is again your nucleophile you are having at the ortho, and at the para position you can see we are having the electron withdrawing group. So addition then elimination reaction will be taking place. So again the nucleophilic substitution it will be taking place, and you will be getting is this particular species here, the OC2H5 it will be present, and here at this positions your NO2 groups it will be present. So this is the desired product I guess that we wanted, that is 2,4, that is ethyl 2,4 dinitrophenyl and the ether molecule. So you can see this is the correct answer that we are getting it. So the correct option it becomes the option B. Through the part C and D also you can check it, you will be not getting your desired products. Okay, so B is the correct one. Let us move up on to the next question, that is this one. So we have to find the number of 1-2 rearrangements that are taking place in the following transformation. Okay, so the species is something like this. Here I am having is this OH molecule, and here is this methyl group it is present, and to this position this 4-membered rings have been attached over here like this. This is the species, but complex one it is given. So this is the one. Okay, so here you can see this is treated with the uh, COCl2 in the presence of the pyridine it has been treated. So it is again it is used to convert basically the OH to make it to a good living group. Basically it is used. Pyridine basically it comes and abstract the protons from here, and this COCl2 it turns it into the chlorine species, and that can leave easily from the medium. So here you will be getting a formation of the carbocation species it will be formed, because this is used to convert it into a good living group. So here again this 4-membered ring. So we are getting is this particular species. Here this 4-membered ring it is present. Here also this. Okay, so this is again your 4-membered. Here also this 4-membered it is present. Here also this 4-membered and this 4-membered. At this particular site, this is the carbocation it will be formed. This is gonna convert this OH to a good living group. So after that this carbocation will be formed. Now this 4-membered rings are present over here. So these can undergo the rearrangement, or the ring opening will be taking place. So the strain from this ring it will be released from here. So this is the alpha position and this is the beta. Alpha beta bond breaking it will take place, and the ring expansion you will be observing it. So this is the first 1-2 rearrangement we are doing in this case. So you will be getting here the formation of the 5-membered ring. So here this position the 4-membered it will be present, and here is this 5-membered ring has been formed over here. So 1, 2, 3, 4, and this is the 5th one. Okay, so we are getting something like this. 1, 2, 3, 4, and 1 carbon extra has to be drawn over here. This species it is being formed at this particular site. Here the methyl group that has formed. This is the alpha center, and at this position the positive charge it has been formed. These 4 membered rings they are remaining as it is at this particular position. Right, so this is the first 1-2 rearrangement we have done it. Again you can see this is the alpha position, this is the beta. This alpha beta bond breaking you will be seeing, and the ring expansion you will be doing it. Again you can do the 1-2 rearrangement in this case. So this will result into the formation of again a one new 5-membered ring you will be getting. It will be formed over here. So this one we were having. Okay, this one what we got. Now the next 1, 2, 3, 4, and the 5th carbon center, this species you will be getting. So you can do this ring openings and you will be getting this ring, it will be formed. Okay, so again the positive charge it is coming on this carbon center. So again this 4 membered rings are present on this particular 3 carbon centers is present as it is. Again we can do the 1-2 rearrangement in this, because the next carbocation that is present, this is at the alpha and beta position. Again the ring opening will be done. So again one more 5-membered ring you will be getting. After that the positive charge it will come on this particular side. Again this is alpha beta. Again it will be done the 1-2 rearrangement. So that will be the next one. I'm not drawing the 5-membered rings again and again. I'm just counting the number of 1-2 rearrangements. So this one again it will take place. After that positive charge will be coming on this side. Again you will be doing it. The ring opening, again 1-2 rearrangement will give you the desired product. So the after that the elimination will be taking place. So alkene will be formed over there. So how many 1-2 rearrangements we have done? 1, 2, 3, 4, and the 5 one. So to open 5 of this 4-membered rings that was given to us. So 5 of the 4-membered rings were given. So 5 rearrangements it will be taking place in this. So the correct answer will be the option C for this one. So you can do the openings yourself. I have told you the mechanism. How is it gonna proceed? Okay. So now let us move on to the next question, that is this one. So in this we have been given as a diol type of the species. So like this the species have been given to us. This is my 4-membered ring and this is the another 4-membered ring, and here is this 2 of these OH groups are present on this. Okay, so now this is firstly treated with the acidic medium. So what is this acid gonna do? It will be protonating one of this OH group that is present over here. So this oxygen it will be protonated. So we will be getting as this species OH2, and this is converted into the positive one. So this is gonna leave from the medium, resulting into the formation of the carbocation like this. This species we will be getting. Here the positive charge it will be present. Right, now on the alpha position you can see there is this OH group which can apply the plus M effect and can stabilize the carbocation, and along with that the 4-membered ring that is present, it is your strain system. So it will be after the ring expansion we can do in this, because that strain it will be released in this. So this is alpha beta bonds electron density it will be shifted. Beta will be forming the bond and alpha will be carrying the positive charge with it. So this is the 4-membered ring we are getting, and this 5-membered, this fused ring you will be getting. Here you are having is this OH group, and this was the alpha position. So the positive charge it will be coming over here. It can apply the plus M effect over here. So we will be getting is this species. So a bridged system containing the 5-membered ring with the 4-membered ring and this ketone group. So this is after the first step you are getting your species. Next is the treatment of this. It has been done with the lithium aluminium hydride, which is my reducing agent. So it is gonna convert the ketones to the secondary alcohols. So we will be getting is this species. Here now OH molecule it will be formed over here. Right, in the next step again they have treated this with the acidic medium. So now in this time the OH molecule again it will be protonated like this. and it will be forming OH2 and the positive sign it will be present, and this four membered ring it is present. Now this water it can leave from here, resulting into the formation of the positive charge at this particular site, and this four membered ring it is present. Right, now four membered ring it is your strained ring, so a ring expansion it can take place in this. So this is my alpha and this is the beta. This bond breaking it can take place and the ring expansion it will be taking place. So that is gonna give us this particular species. Here the five membered ring and the other five membered ring it will be formed over here. So we will be getting is 1 2 3 4, 1 2 3 4, and this is the five membered ring. You have got it, a positive charge it is coming at this particular site. You can present it at this in this particular format as well. This is the ring and here the positive charge it is present. Now in the final step, this hydrogen atom that is present it is gonna leave and the alkene formation it will be taking place. So this is gonna be our final. Okay, so two of the five membered ring with the double bond in between them, that is in the option A we are getting. So A is the correct answer to this particular question. Okay, so now let us move upon to the next question, that is this one. It says the intermediate which is less likely to be formed in the mechanism. So various intermediates have been given, we have to predict which one is the least likely to be formed. Okay, so here you can see two of the OH groups are present. We will be protonating that OH group that is gonna form the more stable carbocation. So this is the one, that is this after the protonation, if it is getting being lost from the medium, it will be forming our secondary carbocation. So we are getting this type of these intermediate species like this one. This is the one, this carbocation it will be formed after its protonation. I have done it, so it will be leaving from the medium. Right, next is for the rearrangements have been done in this, so you can do this rearrangement. This hydrogen atom it is gonna leave from the medium, so this positive hydrogen atom it will be shifted and the positive charge it will be coming on the next carbon center. Right, so this species it is present, here is this OH group and the positive charge is coming on this carbon center. Again we can do the 1-2 rearrangement because oxygen molecule that is present, it can apply the plus M effect over here. So you can do the again 1-2 shifting. Here the OH group, here it will be the positive charge and here this ethyl group, the rest of the substituents it is present as it is. You can count the number of the carbon atoms if I am making some mistake in this, so you can do the correction of that. Okay, 1 2 3 4, 1 2, here it will be one more. Okay, so this is the species. Now for the plus M effect it will be applying and you will be getting your desired species. Right, so this is the, it will be converted into the aldehyde molecule. So this is the complete mechanism that is being followed over here. Among this you have to see the intermediates that have been formed. In the molecule A that is given, that is your secondary carbocation. So this one is getting being formed during the reaction. Right, next is B1 that you can see, this is the another intermediate. You can see again this was being formed in the reaction. So this is again not your answer because we have to choose the one that is least likely to be formed. Okay, in the C molecule it is formed, that this OH containing this carbocation, this intermediate was formed. So this is again getting being formed during the course of reaction. The one that is not getting being formed is the option number D. Here it is forming the primary carbocation and that is not gonna be formed in this particular case. This is formed, they are doing the protonation of the other molecule. In the starting of the reaction you have to proceed in such a manner you are getting a stable carbocation formation. Okay, so D is the correct answer to this one, that is the least likely carbocation to be formed. Now moving upon to the next question, that is this one. It says the product formed due to the neighboring group participation in the following reaction. Okay, so a species have been given to us. This is in the cyclohexane form. We can draw it into the chair conformation. That is like this. Here at the bulky position, that is this acid chloride group is present at the wedge position. Okay, and at the dash position is this OCH3 group that is present over here. So we can place it like this one. The above side is the presence of this C double bond O and this Cl group it is present, and leaving one of the carbon atom, and at the dash position we are having is this OCH3 group that is present over here, and this we are treating it with the Cl negative, that is this nucleophile has been added over here. Okay, so just make a small correction in this, there is error in the printing. So here is this OCH3 group is not at the dash, rather it is at the wedge position, because NGP at the dash position it is not possible, right? Because it's directly given in the question that NGP effect is being applied. So OCH3 is in the wedge position, so it is in the upward direction. So now we can see this OCH3, this oxygen atom that is containing the lone pair of electrons, it can apply the NGP directly. This electron density will be shifted coming back, and this Cl negative it is gonna leave from the medium. So we will be getting is this particular species being formed over here. So here you are getting is this carbonyl species. This is attacked by this oxygen center that was attached over here, and this is this CH3, and this is gonna carry the positive charge because oxygen has donated its electron density. Now next step they have treated this with the Cl negative. So Cl negative, now it can attack on this particular site, and this electron density it can be shifted. So we will be getting is this particular species. Here this C double bond O and this OCH3 group it is formed at this particular site, and at the dash position this Cl group it will be present. So you can draw it into the chair conformation, that is gonna look like this. So at the wedge position I am having is the presence of this ester species C double bond O and this OCH3, and at the third carbon center the Cl group is present in the downward direction, that represents it is present in the dash conformation. So this is the product that I am expecting, and that I can see it is in the option number A. I am getting it. Okay, so A is the correct answer to this one. Now let us move upon to the next question, that is this one. So again a reaction has been given, we have to predict the product in this. So isotopically labeled bromine has been given to us in this particular molecule. Okay, so this is Br, that is isotopically labeled one. So this species it is treated with the bromine water, so Br and this Br group. So firstly the brominium ion it will be formed over here, so you will be getting is this type of the species, right? And here is this Br, that is isotopically labeled one, it is present as it is. Now you can see intramolecular attack it is possible like this, and this ring it can open from here. So we will be getting is this species. So a more substituted site, the Br group it is attacking. So this species we have got it. This is gonna carry the positive charge, and this one is CH2 and Br it will become. So this molecule we are getting. Now in the next step we can do the attack of the water molecule. So water it is again gonna attack on the more substituted site, that will be at this particular position, and this ring it will be opening from here. So finally the species that we are getting is like this. Here the bromine, that is 82 isotopically labeled one, it will be coming. Here it will be this OH molecule that has attacked, and CH2 and this Br group it will be present. So this is the final product that we are getting. So you can see it from your options, isotopically labeled bromine, then the OH and the Br. So this is in the option C we are getting it. So the correct answer is the option C for this one. So this is the last question to be discussed in this particular video. So with this we have covered approximately now 120 questions of this organic portion. We are done with that. I hope all these questions that we have discussed so far are clear to you. But if you still have any doubt in any of the questions that we have discussed so far, that you can ask me in the comment section. I'll surely reply to that. And if you have come till here, I hope you have understood the concepts. So make sure you hit the like button for the video, and do subscribe to the channel also, so that you can get notification of the upcoming parts to this particular series. So thank you so much for this. Meeting you in the next video now with the remaining questions that we will be covering in the next part now. Okay, so till then, bye bye.